1988, I wrote a popular science book called A Brief History of Time, which sold over 10 million copies. I say that not to brag, but to underline the deep fascination we all have with our universe.
Years ago, people rushed to buy physicist Stephen Hawking's book. The public were drawn to Hawking because he's a mega brain trapped in a body that doesn't work. He said he would tell us how the universe worked and how it began. But Hawking is now almost completely paralyzed. These programs are a journey into the mind of Stephen Hawking and his lifelong quest for a theory of everything. Stephen Hawking's record-breaking best-selling book, A Brief History of Time, has made him an international celebrity. But time is precious to a man who clicks out sentences at 3 words a minute. Being a celebrity can have its drawbacks.
This is our fans. Professor Hawking's fans. Huge, incredible piles of mail. Their imaginations are extremely interesting. You get people who write in about time wormholes and about spacecraft, alien invaders, teleporting. How can Professor Hawking possibly comment on all these theories? It's not possible, but we do try and interest some of the students sometimes.
Slowly, word by word, click by click, Hawking is inching towards a complete theory of the fundamental processes of our cosmos. His theory of everything. His focus now is the very moment of creation, the birth of our universe. But to crack that involves making sense of the least understood force in nature.
My recent experience of weightlessness demonstrates how well we understand gravity on a human scale. But we must understand gravity as it affects individual particles.
Stephen Hawking is like a cosmic crime scene investigator. He's trying to understand how the Big Bang happened 13.7 billion years ago. He's turning over all the remnants of the explosion and trying to fit them back together again. The fragments are all the matter and forces of nature we see around us today. But one piece does not want to fit. Gravity. As human beings, we don't notice anything strange about gravity. But if it had been any stronger, the universe as we know it could never have existed. Space would have been pulled back in on itself, obliterating any possibility for planets and stars to form. Our universe was only able to exist because gravity is so bizarrely weak. As physicist Michio Kaku explains,
we see 4 fundamental forces of the universe today. Gravity, which holds the Earth, the Sun, and the solar system together. The electromagnetic force, which lights up our cities and the internet and laser beams, and also the two nuclear forces. Well, why should there be four fundamental forces? We think that at the instant of creation, these four forces meld together into a single force, a superforce.
At the Big Bang, everything was one. But as the universe cooled, four forces emerged. Electromagnetism and the two nuclear forces, which control atoms and radioactivity, they all seem to be about the same strength. But the fourth force, gravity, refuses to join the club. Professor Lisa Randall of Harvard University is a physicist who, like Hawking, is trying to bring gravity into line with the rest of nature.
It turns out that gravity is many, many orders of magnitude weaker than the other forces. And certainly gravity doesn't seem that weak when you're climbing up a mountain. But with an incredibly tiny magnet, I can pick up this paperclip with the tiny magnet. Now, is that amazing? Well, this tiny magnet is competing against the gravitational force of the entire Earth. At a fundamental level, the force of gravity is much weaker than the other forces. But the problem is that we don't understand where this huge discrepancy comes from.
This discrepancy is Hawking's tormentor. To finish his theory of everything, he needs to be able to explain gravity at the moment of the Big Bang, when the universe was tiny.
If we want to know what happened when the universe began, we have to have a theory that can describe gravity on a very small scale.
Hawking has struggled for decades to solve this problem, but he's not alone in his quest. The final breakthrough may well come from someone else. In 1988, Stephen Hawking's book, A Brief History of Time, was published. Overnight, Hawking became a household name. He was in great demand. The world waited eagerly for his much vaunted theory of everything.
When The Brief History of Time first came out, I think physicists were fairly hopeful that we would have this final theory of everything, maybe within just a few decades.
In 1988, there was certainly cause for optimism. Only gravity had to be explained and brought into the fold. Back in the 1970s, Hawking had already given physics an inkling of how it might work. He'd proved it was possible to unite the theories of the very large, stars, planets, and gravity, as originally proposed in Einstein's theory of relativity, and blend in some of the theory of the very tiny, of atoms, quantum mechanics. By joining the large and the tiny in a limited way, Hawking had discovered that black holes are not completely black. They must, because of tiny subatomic effects, give off some microscopic radiation. Physicists were fascinated. It was as if Hawking had pulled down a wall. Suddenly, the theorist of the very large and the theorist of the very small had something to talk to each other about. One of Hawking's colleagues at Cambridge, Professor Michael Green, remembers the turning point well.
In the old days, the two groups were very separate. The two groups hardly spoke to each other until, I think, essentially Stephen's very important work in the mid-70s, 74. And I think that's a key point at which these two very separate kinds of disciplines started to come together.
The race was on. If Hawking could find a connection between the large and the tiny in black holes, could there be more? Surely a single theory of the universe could be found that would include how gravity worked, both now and when the universe was tiny. Hawking and many others fought to expand his ideas. When A Brief History of Time came out, the frontrunner for a theory of everything was a theory called supersymmetry. Supersymmetry is based on the idea that when it was extremely tiny, everything in our universe, including gravity, was merged into one almighty superforce.
We think that at the instant of creation, there was a superforce, a master force, a single force that governed the properties of this dot-like universe. But then the universe began to expand, and the force cracked.
When the universe began, the superforce was entirely symmetrical. It was made of the same stuff, and it all behaved in the same way. But then, as it expanded, this symmetry started to break. As differences in the force crept in the milliseconds after the Big Bang, different aspects of the universe started to form: matter, space, forces. Gravity started to become distinct from the rest of the universe. Gravity, and all the other parts of nature we see today, are the irregular, imperfect descendants of the original superforce.
The world we see today is very unsymmetrical. We have mountains, valleys, we have rivers, planets, stars. It's not very symmetrical at all. So the symmetry has been broken. So the reason why the symmetries of the universe today are so broken is because the universe is old. But at the instant of creation, 13.7 billion years ago, we think the universe was whole, coherent, one, with one superforce, glued together by supersymmetry that typified the early universe.
The theory of supersymmetry solved part of the problem Hawking had with gravity. Now the whole of nature, including gravity, could be unified at the Big Bang by one set of equations. But there is still a problem. If gravity was unified with everything else at the Big Bang, why did it become so very weak afterwards compared to the other forces? The brightest minds like Hawking and Professor Ed Witten were trying to work out how the perfection of supersymmetry broke and ended up as the world we see today.
Imagine sitting down at a dinner table. There's a glass to your left, and there's a glass to your right. So the arrangement of the table has a symmetry between left and right, at least for the glasses. It works fine if everybody picks up the glass on the left or if everyone picks up the glass on the right. But a mixture where everybody sits down and ends up with the glass breaks the symmetry. You all pick the glass from the left or the glass from the right. That's an example of what physicists call spontaneous symmetry breaking. And it's ubiquitous in the real world, both for the electrons in a piece of iron and for the early universe settling down from the Big Bang.
It was not clear why the universe had settled down the way it had. Supersymmetry seemed to be only half a solution. For Hawking, the problem of gravity's weakness remained. As Hawking and others inched closer and closer to a complete theory of everything, his ability to communicate was slowing down drastically.
I'm going to demonstrate using a hand switch, which is what Professor Hawking used to use until about 2 years ago. Now, he uses a menu system, which is basically a big screen full of words. And when he presses the switch once, you see this highlighted section that goes up and down. That's actually selecting which part of the screen he wants to speak from. So if you press it and then press it again while it's over the top half, it's now worked out that he wants to say something in the top half of the screen. And if you press it a third time on the right line, it'll go along that line, and a fourth time lets you select a letter. And now we've got a whole screen full of words beginning with Q and R. And you can do the same thing again, and you can select a word. That's how he builds up a sentence, word by word, or if he wants to speak a word that isn't in the list, he can do it letter by letter as well.
Throughout the 90s, at only 4 words a minute, Hawking worked away at the problem of gravity. But in that time, cutting-edge physics became extremely dependent on complex maths. Hawking was reliant on students and colleagues to perform computations.
Thank you very much.
And the next big breakthrough came not from Hawking, but from a colleague just down the corridor. Professor Michael Green is one of the big hitters in what is known as superstring theory, or string theory for short. It suggests that all the particles and forces of nature are actually vibrating little string-like objects. And it seems to magically solve the problem of gravity that Hawking was struggling with.
One of the remarkable things about string theory is that it necessarily includes gravity. And in fact, in the earliest days of string theory, people were trying to formulate a theory which did not include gravity. They didn't understand that string theory necessarily included gravity.
String theory is a radically different way of looking at our universe. In string theory, the entire universe, including space, time, and even gravity, are made of tiny, string-like objects that only appear to be different particles because of the different ways they vibrate. Our world is just a giant mesh of vibrating strings. And the beauty of string theory is that it unifies the theory of the large and the theory of the very small.
First of all, each vibration of the string corresponds to a particle. Therefore, string theory is a quantum theory. The jumble of particles we see is nothing but the jumble of notes vibrating on a string. But when the string moves in space and time, it forces space and time to curl up. And that's why we have precisely Einstein's equations.
Because string theory can encompass both the tiny quantum world and the vast world of space, it looked like it might hold the answer to the problem of gravity that was so tormenting Hawking. But it was not Hawking who saw the possible solution. It was that chap down the corridor, Michael Green. Here in Aspen, Colorado, he and his colleague, John Schwartz, finally cracked how to make gravity fit the theory.
We were making progress, we felt, in understanding how string theory, or symmetrical string theories, which we call superstring theory, to understand how superstring theory works. But in the early 80s, there was very little interest in our work. People were pursuing other, somewhat related, but other directions. And so we were convinced that what we were doing was quite important, and we found it rather puzzling that there wasn't more interest from our colleagues.
It sort of culminated, as I remember it, essentially in one day, when suddenly everything fell, all the pieces of the jigsaw puzzle came together, and it was a really unusual feeling for both of us.
Green and Schwartz had made a huge breakthrough.
When the news came of the Green-Schwartz calculation, that was like a thunderclap, and I was pretty sure life would never be the same again, at least not professional life.
Green and Schwartz's version of string theory not only included gravity, but it had an amazing explanation for why gravity is so weak now. The reason? The universe is made up of 11 dimensions. It may sound like science fiction, but even Stephen Hawking is prepared to admit it might be right.
String theory is the only candidate for a theory of everything that has a certain symmetry that physicists believe in, but have not yet observed. If it is not found, we will have to think again.
If gravity is operating in 11 dimensions than just the 3 we see, it's not surprising it's so much weaker than the other forces. Stephen Hawking has spent 45 years trying to create a theory of everything. His main stumbling block has been finding a way to explain how gravity arose in the white heat of the Big Bang and why it's so weak. Now the elusive answer seems to have come from elsewhere. String theory has been developed for 20 years now. The latest version is called M-theory, and almost all physicists have huge hope for it as a theory of everything. But to explain gravity's weakness, the theory has to be constructed in 9, 10, even 11 dimensions. It sounds like science fiction, but string theorists believe those extra dimensions to be real. In fact, they seem to be all around us.
String theory, in addition to the 3 space dimensions that we're familiar with, sideways, up and across, there are some extra dimensions. In the simplest versions of the theory, we say there are 6 extra dimensions. which we don't see directly in the physical world. But nevertheless, they could be there.
We don't notice the extra dimensions because they're outside our 3D universe. Some could be bigger than our 3 dimensions. Our entire universe could be sitting inside a higher dimension. We're a bit like fish in a tank, unaware of the world outside, unaware of the extra dimensions.
Today, we physicists believe that we are the fish. We spend all our lives in 3 dimensions, going forward, backward, left, right, and up and down, not realizing that there could be other dimensions, other universes, other ponds, perhaps as many as 11 dimensions in a multiverse of universes. Some people say, well, what's at the edge of the universe? Is there a wall that says the end of the universe? Do not pass go. This is it, folks. The answer is no. Think of the way Columbus handled that question. People said, Columbus, if the earth is round, then what happens when you fall off the edge? And then Columbus said, there is no edge, because you just keep on going around in a circle. So in 2 dimensions, the earth is infinite. You can spend all your time going in a circle. But in 3 dimensions, the earth is a ball, is finite. In the same way, our universe looks infinite in 3 dimensions. You can go anywhere and there's no wall out there. But in 4 dimensions, in hyperspace, perhaps it's just a pond.
But extra dimensions do not have to be bigger than our 3D universe. Some could be tiny. They could be curled up so small we don't notice them. And that may explain why gravity is so very weak, if Harvard professor Lisa Randall's work is correct.
So it could be that at every point in space there are these curled up extra dimensions, looking somewhat like these donuts do. Now, it's a little hard to imagine because the whole idea is that if there are 2 curled up extra dimensions and it's curled up into the shape of a donut, or we call it a torus, there could be one of these donuts at every point in space, and it could be a higher dimensional donut, which is hard to draw and even harder to eat. But it could be that there are even more curled up extra dimensions in this way. And that what this illustrates is that at every point in space we have one of these donuts.
And we may not have seen these extra dimensions because they are too small for us to measure.
No, thank you.
To us, they might just look like points in space.
So if you look over there at that garden hose, you see that it pretty much looks one-dimensional. So now that we're holding the hose and right next to it, we see that it's not one-dimensional. We see a lot more structure. We see a lot more detail that we couldn't see before. When we're far away, we see this metal tip. We see that it actually has this 2-dimensional surface and a 3-dimensional interior. Of course, we knew about that before, but now we could, if we wanted to, we could do experiments. We could have something inside where we actually probe this 3-dimensional structure. But what we're learning seems so obvious, but it's actually something very fundamental in physics, which is how you describe something depends on what your measurement tools are.
Physicists now believe that what looked like the tiniest, immeasurable small points in space may actually conceal curled up extra dimensions. And that would affect how we perceive gravity. The idea from string theory is that gravity is not weirdly weak after all. It just looks weak. It may be just as strong as all the other forces in the universe, but its effects are weakened by having to make its way through extra dimensions. It's a bit like distant music fighting its way through a noisy environment.
Maybe that's why gravity is so weak, because most of gravity flies into hyperspace and disperses, and we only see the remnants. That's why when you hear this music, it's very, very faint, because most of the music is gone in a different direction, and we only hear the remnants.
Extra dimensions act a bit like a sieve. Up close to the tiny extra dimensions, gravity is strong. But as you move away, it gets very weak very quickly. The final piece in the theory of everything is potentially hovering over the last hole in the jigsaw. The Holy Grail is within reach. It seems that gravity is as strong as all the other forces in our universe, but just feels weak because it's fighting its way through extra dimensions. The trouble is nobody, not even Hawking, has any idea whether any of this is true or not. Supersymmetry, string theory, M theory, extra dimensions, they all exist on paper. There is a little evidence that some of the particles predicted by supersymmetry exist. All that actually exists are very elegant theories, but no hard proof. But Hawking remains optimistic evidence will be found.
Particle physics has made fabulous advances in the last 20 years. By colliding particles at the kinds of energies that would have been around at the Big Bang, we have unified 3 of the 4 forces. Gravity still refuses to be tamed. But, perhaps, not for long.
And the proof may come from here, at CERN, near Geneva in Switzerland. They're building the biggest experiment ever conceived. The Large Hadron Collider works by firing subatomic particles in opposite directions around a 16-mile tunnel. They hit each other at nearly the speed of light. The energies involved replicate the conditions that were around in the early universe. In theory, the machine is not quite powerful enough to explore what gravity was like at the exact moment of the Big Bang. Or is it?
Trying to unify gravity with the other forces in nature would involve an experiment with incredibly high amounts of energy. That would be far beyond the capacity of any machine we have ever built. But if string theory is correct, help may be on hand from extra dimensions.
Amazingly, there is an outside chance that we will see extra dimensions at CERN. And that puts Stephen Hawking's own work back center stage.
So you might ask the question, is it possible that by colliding particles in an accelerator, you could actually produce little black holes?
Black holes can be any size. They can even be the size of an atom. If string theory is right, and strong gravity from other dimensions is real, then incredible things might happen at CERN. 2 colliding particles would get an extra squeeze from strong gravity. They'd become ultra-dense, and if that happens, they'll collapse into a microscopic black hole.
Once you get within the distance associated with these extra dimensions, then gravity goes up more fast as distance decreases. And that's what's allowing you to form the black holes more easily.
And Hawking's work on black holes predicts they would explode very quickly.
And if the black holes were formed in the Large Hadron Collider, they would be very noticeable. It's been said that they would shine like a Christmas tree, and you would be able not only to detect the black holes, you would be able to detect the evaporation of the black hole as predicted by Hawking.
Such a result would be a double whammy. For the first time ever, there would be experimental evidence to back up Hawking's theories about black holes. Hawking might even get a Nobel Prize. And there would be strong evidence that extra dimensions are real, and that string theory is really on the road to a theory of everything.
You would produce extra particles that can travel into the extra dimension. And if we see those particles, it would be strong evidence that these extra dimensions actually exist.
The big switch on at the Large Hadron Collider is waited for with bated breath by the whole of physics. It might well fundamentally change our view of our universe and shed light on the big questions that Hawking has always sought answers to. For Stephen Hawking, it will be yet another reminder of our true place in the vast cosmos.
We once thought we were at the center of the universe. Then we thought the sun was. Eventually we realized we were just on the edge of one of billions of galaxies. Soon we may have to humbly accept that our 3D universe is just one of many multi-dimensional worlds. Can we now say where we came from and where we are going? I'm tempted to say that science is about ever-expanding horizons, and that new discoveries only help us to frame questions in more and more accurate ways. However, there is more to the answer than that.
Stephen Hawking is dogged in his determination. He's lived 45 years longer than his doctors predicted. He is now divorced for the second time. He may become totally paralyzed. None of it phases him.
I think Stephen faces in his thoughts absolutely every scenario he could possibly face. He's not afraid of any scenarios, really. I mean, he's an incredibly brave person and a huge risk taker. You know, he's got a really incredible appetite for life.
Just about the only area in his life where Hawking is a stick in the mud is his world-famous voice. It's a voice that was cobbled together from a 1980s telephone answering system.
The card was actually first designed for a sort of automated telephone use. This was back in the 1980s when that was a really, really difficult thing to do. And it was a cutting-edge synthesizer at the time.
Can you finish in 10 minutes?
In 10 minutes. He could have a voice that is more realistic, more easy to understand, and would use less power and wouldn't break so often. But the one he has is recognized all over the world, and it's the one he wants to keep.
Thank you very much.
So after a lifetime of trying to answer the big questions about existence, what does the universe look like to Stephen Hawking? How does he think it began? Remarkably, he's one of the few scientists who've tried to do more than compute what happened at the Big Bang and how it evolved afterwards. He's proposed why the Big Bang happened in the first place.
The universe is governed by two kinds of laws. Laws of evolution, which determine how the universe develops in time, given its state at one time, and boundary conditions, which determine the initial state. So far, almost all scientific effort has been devoted to finding laws of evolution, but Jim Hartle and I proposed the no boundary condition as the only reasonable initial condition for the universe.
Hawking's no boundary condition is his most radical suggestion to date. It's a proposal, not a theory, but it's based on strong science. Hawking's universe did not have a beginning, but bizarrely, it has also not existed forever. The best analogy Hawking can give is that of bubbles, but without the man to blow them up. The universe spontaneously arises. Time begins when the universe begins. It goes on expanding, perhaps forever. In Hawking's mind, our universe has no creator. It came out of nothing and exists all on its own. It's the ultimate free lunch. Although Hawking did think of making some cash out of it.
Maybe Hartle and I should have patented our idea and have charged everyone royalties for their existence.
And interestingly, many within physics are coming round to Hawking's radical view. Within the 11 dimensions of string theory, some scientists think our universe could just be one of many 3D blobs. In string theory, it's possible that there may exist entirely separate giant sheets of space. String theorists call them membranes, or brains for short. 3D universes can form on brains, a bit like water globules forming on glass.
It could be that matter, stuff we know about, is actually stuck or lives on the surface of a brain.
And the idea that we are stuck to one of many membranes raises the distinct possibility that membranes may clash out there in the greater universe.
If we are just one brain, maybe there are many other brains.
There could be other brains elsewhere which we're unaware of.
And so each of these brains would in some sense correspond to a different universe, and maybe these brains may occasionally collide.
One of the ideas that's been proposed is that the Big Bang explosion 14 billion years ago originated as a collision of brains.
Not only is it possible to make such a theory, but it's got some attractive features, because it can explain why gravity appears to be so weak.
It's all pretty heady stuff. It's the kind of thing physicists dream about. And it's all a long way off from being proven. But if you don't dream, if you don't search, Hawking would argue, what's the point of life?
During my lifetime, we have discovered many of the laws that govern the universe, but we don't yet understand how they all fit together, or why they seem to be finely adjusted to allow life. I'm confident that we will resolve these mysteries. and I think the years ahead will be a golden age of discovery.
Stephen Hawking may not have single-handedly created a theory of everything, but he's come within a whisker. He may be stuck in a wheelchair, but that hasn't stopped him being a tireless explorer. Soon the master of the universe is off on his travels again. Hawking plans to be on the first commercial flight out into space. As always, there's a reason for his adventure.
I think we are acting with reckless indifference to our future on planet Earth. At the moment, we have nowhere else to go, but in the long run, the human race shouldn't have all its eggs in one basket, or on one planet. I just hope we can avoid dropping the basket until then.